You ever been in class and your teacher says, today we're going to be talking about chemical reactions, and you're like, well, what's a chemical reaction? Well, there are many different types of reactions, and what we're going to do in this particular video is we're going to talk about double replacement reactions specifically. But before we get to that, I want to just kind of introduce you to some of the main types of reactions that you'll be looking at in your chemistry class. So one reaction that you would look at is called a synthesis reaction. And synthesis reaction is also called a combination reaction, where you take two different elements. In this case, we take A plus B and we produce AB. Another type of reaction that you might study is called a decomposition reaction. A decomposition reaction is just what it says. It's where the compound breaks down. So in this case, we would take AB, and AB breaks down to A plus B. In this case, it would break down to its elemental components. And there are various types of synthesis and decomposition reactions, but we're not going to focus on that in this video. There's a third type, which is combustion. Combustion reactions are basically where you take a hydrocarbon and you react with oxygen gas and you produce water and CO2. So the generic formula for a hydrocarbon is CXHY. It's going to react with oxygen gas and it's going to form these two products here. Now, a fourth type is single replacement. Single replacement reactions are going to be where you have A plus B. See, this is the generic formula equation. A is going to replace B. It's called single replacement. One element is going to replace the other, but here's where the thing is, that requires activity series, and that's something we'll talk about in a separate video. So, but A replaces B, and so you form AC plus B. Now, the reaction that we're going to focus on today, which is the fifth one, is double replacement. All right, so we're gonna start here, and this is where we're going to spend most of our time today. So, double replacement can be also known as metathesis. Let's talk about the generic formula for double replacement. So, double replacement is where you take AB plus CD. So in this case, you have two elements, AB, and you have two elements, CD. Now typically, A is a metal, and then B is a non-metal. Same thing with C, which is a metal, and D, which is a non-metal. Now in this case here is where you have a switcheroo take place. They just switch with each other. So A replaces C and reacts with D. So you form AD, and then C reacts with B, and so you form CB. Now, one important note here is that you always want the metal to be first, and then you want the non-metal to come after that. That's the way an ionic compound is written. You don't want a metal to metal or a non-metal. You want the metal first and then the non-metal. So in this case here, again, A is your metal, and then CD was our non-metal, and the same thing showed up for these two here. So now there are three types of double replacement reactions. The most common one is precipitation. The second one, and this is fairly common too, and everyone has heard of this, it's called neutralization. And then the third one is gas forming reactions. We're going to focus on these two today, precipitation and neutralization. So what is precipitation? Precipitation is where you have two separate compounds. When you put them into a solution, they react together and they form a precipitant. Now, what exactly is a precipitate? Precipitate is a solid that falls out of solution. And so you have to ask the questions. How do I determine which is a solid? That refers back to the solubility rules. So the solubility rules help to define whether a compound is soluble or insoluble. And so those are two key words here. Soluble means that it will dissolve into solution, and then insoluble means that it will not dissolve into solution. So, solubility rules, I'm going to put this image on the screen here in just a second. But these are the solubility rules, and there's two different categories for the solubility rules. There's soluble, and then there's the insoluble. And so the way this works is, if you're in the insoluble category, which is in the bottom, or if you're looking at the soluble category, anything that's in those two different spaces are going to be either soluble or insoluble, unless it's the exception. So let's look at the soluble category, for example. So if you look at the soluble, so let's say we have a compound. Let's say we have silver nitrate, AgNO3. So you look at this compound, AgNO3. Well, so we find that the nitrate is in the soluble category, and there are no exceptions. What does that mean? That means that silver nitrate is soluble in solution. Now, if we look at a different one, AgCl, so we find the Cl is in the soluble category, and we look at the exceptions. The exception says salts of silver, mercury +2, or lead +2. Well, we see that this has a silver, that's the exception, therefore that exception makes this compound insoluble. So, as you're working with the soluble category, all right, you got to pay attention to the exceptions for those salts. Now, if you go to the insoluble category, well, anything that's in the soluble category is insoluble unless it's part of the exceptions. So, let's say we take Na2S, which is sodium sulfide, and say, okay, well, is that soluble or insoluble? Well, we look at the rules. It says sulfides are insoluble except with salts of NH4+, which is ammonium, the alkali metal cations. Okay, so go back to your periodic table and you say, okay, well, which group is the alkali metals? It's in group 1A, and if you notice, sodium is in group 1A. That's one of the exceptions, so therefore this compound is going to be soluble. Now, if we take calcium carbonate, CaCO3, okay, well, fine carbonate, right, carbonate is in the insoluble category, and it has salts of ammonium and the alkali metals. So we go back to the periodic table and see, okay, calcium is not in group 1, it's not an alkali, it's an alkaline earth, therefore this compound is insoluble. That's important because when you go up here and you start looking at your products, AD or CB, you're going to be looking at the solubility rules on the periodic table and try to determine if one of those are precipitates. Now here's the thing, if they're both soluble in solution, then we would say that there would be no reaction occurring because we don't see anything happen. And so that's the important detail here. Now let's look at a few examples and keep your solubility rules out and keep your periodic table up, just so that way you can follow those and you can look at them as we go through these few examples. All right. So the first example we're going to look at, and this is one that you see quite often. Your instructor might actually use this in lecture, is where we take silver nitrate. It's in solution, and we put it with sodium chloride. which is also in solution. Now, when we talk about solution, we're talking about something that's already dissolved into a beaker. So we'd have 2 beakers of solution, and in this side here, we'd have silver ions and nitrate ions. In this one, we would have sodium ions and chloride ions. Now, what we do is we pour the sodium chloride into the silver nitrate. And so over here in the products, this is what our goal is. We're trying to figure out, is there going to be a precipitate forms? If we see that there's a precipitate forms, then yes, a reaction took place. Now, in this particular example, we do see a precipitate form. In fact, the precipitate fell out. So now what we're going to do is we're going to figure out what the products are, and we're going to figure out which one of those products are the precipitate that's fallen out of solution. So now, just like we did before, this is A, this is B, this one's C, and then this one is D. So A is going to go to D, and C is going to go to B. Now, we have to pay attention to the charges of the ions as we do the crisscross, as we replace each. So the silver is +1 charge on this side. The nitrate's -1. You can go back and look at your periodic table or polyatomic ion list to find that out. This is +1 and this one's -1. So when we carry this over together, we're going to have AgCl. All right, Ag is +1, Cl is -1, so it's already balanced out, so that formula is neutral. Always have to balance the equation and write the formulas correctly. And then we're going to form NaNO3, and we can see from over here that this is the nitrate is -1 and the sodium is +1, so those cancel out. That's neutral. Now what we want to do is we want to figure out which one of these salts are insoluble. Going back to our solubility rules, what we want to do is we want to find that we can look at the chlorine that's in the soluble category. Just like the example we saw earlier, the silver is an exception, therefore making the silver chloride the precipitate. So we can abbreviate that as PPT or as a solid, and a lot of times you'll see the S represent the solid in this case. So that's your precipitate. Now let's look at this and see what the NaNO3 is. So it says in the solubility rules that nitrates are soluble. There are no exceptions. Therefore, this is going to be soluble, and the symbol for using soluble is aqueous. Write this down. So if you are soluble, you'll write AQ. If you are insoluble, you'll write solid or PPT. This is the more common way. So that's one example of a double replacement reaction. All right, so let's look at another example. So in this example, what we're going to do is we're going to take Na2SO4. We're going to react it with CaCl2, calcium chloride. All right, so take a second, go ahead and do your crisscross and figure out what your products are going to be. This is A. This one's B, this one's C, and then this one is D. So we're going to put NaCl, so we're going to form NaCl plus CaSO4. All right. So let's look at the charges and make sure they're balanced out correctly. So Na is +1, basically going back to periodic table, looking at the charges. This is -1. Calcium is +2, and then sulfate is -2. So those balance out automatically as they're written. The other thing we want to do is balance the equation. So to balance the equation, we would put a 2 in front of the NaCl. Now, the next thing we want to do is go back to our solubility rules. We want to figure out which one of those two are going to be a precipitate, if there is a precipitate. And so we look at NaCl and we see that Cl has exceptions of silver, lead, and mercury. Na is not one of those, so therefore this one is aqueous. Now let's go to the sulfate. All right, we can see that sulfates are soluble except with salts of calcium. Well, right off the bat we see calcium here, so therefore this is going to be your precipitate, your solid in solution. So these are just a couple examples of how we go about figuring out the products of a reaction, including a double replacement reaction. So this is dealing with precipitation. So the second thing we're going to look at is we're going to be looking at neutralization. Neutralization is our next point. So what is neutralization? Neutralization is where you take an acid plus a base and they react together to form a salt plus water. That is your generic formula that we use for neutralization. So think about what neutralization is. You all have probably seen a car battery that's corroded on the terminals. Well, what do we do to help clean it off? We take Coke or some other solution, we pour it on there, and what does that do? That neutralizes the acid. And so the products that come off of that are salt and water. And so anytime you're dealing with an acid, first of all, what's an acid? An acid is something that has a hydrogen in front. So a good example would be HCl, hydrochloric acid. Another example would be H2SO4, which is sulfuric acid. Another one, there's many different acids out there, but we're just going to stick with a few of them that they're more common, strong acids specifically. All right, this is nitric acid. So all these are acids, and as you notice in front here, they have hydrogens. So oftentimes the hydrogen is what makes this compound acidic. Now, common bases can include sodium hydroxide and potassium hydroxide. There are other bases out there, and then another one would be ammonium hydroxide. So that'd be another example. But we won't work with that one right now. We're just going to stick with the first one up here. So in this case here, we have HCl reacting with sodium hydroxide. All right, both of these are aqueous to begin with. They dissolve into water very easily and readily. And so just like before, it's a double replacement reaction. So the hydrogen goes to the OH and the Na goes to Cl. So you end up forming H2O plus NaCl. It doesn't matter the order that you write the products in, as long as you have the right products. Now, always make sure that the equation is balanced in the end. So we have one hydrogen. Now, when we look at this water here, a lot of times you can write this as HOH. It just helps with the balancing part. You don't have to write it like that. But you have one hydrogen and one hydrogen. You have one Cl, one Cl, one sodium, and then one hydroxide. So this equation is balanced. Now, the last thing I want to do here is figure out the physical states for the two products. And so NaCl, we've seen earlier that that's aqueous, it's soluble. But what about water? What do you think the physical state of water is? It's not aqueous, it's not a gas, it's a liquid. And so in this case, it's a liquid. There are two liquids that form. Water is the one liquid, and then you have Br2, which is the other liquid that could possibly form. We will not be working with Br2 in double replacement reactions. So now, well, we kind of have this set up here. We'll do that last, just for the fun of it. So this here is going to form the same product. It's going to have water plus the salt. In this case here, it's going to have potassium going to the sulfate, so you're going to have K2SO4. You say, well, why is it K2SO4? Because potassium is +1, sulfate's -2. It takes two potassiums to balance out that one sulfate. That's why. So Again, this is a liquid, and this is aqueous. Now, is this equation balanced? It is not balanced. So I'm going to rewrite this H2O as HOH so we can count it easier. So if we look at here, we have two hydrogens here on the H2SO4. We're going to have one hydrogen here, so what we're going to do is we're going to put a 2 in front. That gives me two hydrogens, but it also gives me two OHs. If you look here, there's only one OH. We're going to put a 2 in front of that. That gives you two OHs, and it also gives you two potassiums, which balances us out here. So this will be 1, 2, 2, 1 for your balanced equation. So that would be the answer for the second reaction. Now this is the third reaction. And this is a neutralization reaction, but it also is a gas forming reaction. We're going to talk about that, and that's the last thing we're going to cover here is that. So we have the H going to the OH just like we saw before, and the NH4 is going to go to the NO3. And so this is going to form H2O plus NH4 NO3. And so when you look at this, water is a liquid like before. Now we have this compound NH4 NO3. You can go back and look at your Solubility rules and you'll find out. So come back to the chart. You can find out that the NH4 and the NO3 are both soluble, and that's why it's aqueous. All right, is this equation balanced? 1, 1. All right, we've got 1 and 1, and then we have, all right, so good. This equation is balanced. Now I was talking about gas forming. Well, this one doesn't necessarily form a gas. You could say that this would break down to form ammonia, but not necessarily because it's been neutralized in this case. But when we start talking about gas forming reactions, we have to understand that there are some compounds that break down after they're formed. So that's what I'm going to talk about right now. That's the last thing we're going to look at in double replacing reactions. And so, at least in this part of the video. So if we look at NH4 OH, NH4OH actually breaks down to NH3 plus H2O. So that would be what would happen. So if you have NH4OH as a product in any double replacement reaction, it's going to break down to form these two compounds. Another example would be H2CO3. All right, H2CO3 would break down to form water plus CO2 gas. Now, a good example for that would be baking soda and vinegar. If you've ever taken baking soda and vinegar and put them together, you probably saw bubbles that form. It fizzed. The fizzing action that takes place is caused by CO2 gas being released. In this example here, if you've ever opened up a bottle of ammonia, you know that ammonia has a very strong smell to it. A lot of people do not like it, and that's because it's breaking down continuously, forming the ammonia gas. Now there's one more that we're going to look at here, and that is H2SO3. All right, H2SO3 just breaks down and it decomposes into water plus sulfur dioxide gas. This is a very stinky gas. All right, sulfur gases are always smelling. They typically smell like, eggs that are rotten. Not a very pleasant smell. So I hope you guys enjoyed this part. In the second part of this video, we're going to be looking at various examples while we do those reactions and talking about them. And then finally, we're going to talk about net ionic reactions. All right, thanks. See you soon.